Hi, my name is Scott McMillan, and I'm here to talk about our research project titled Spiral AIML, Co-Optimization for High-Performance, Data-Intensive Computing, Source-Constrained Environments. That's a mouthful, and so is our copyright notice and legal disclaimer. But what is this project really about? It's about writing fast code, and fast code depends on three interdependent ingredients. At the highest levels, it's about algorithms, and for us, it's about the mathematical descriptions of computational tasks that need to be performed. In the middle layer, it's about implementations, and that involves writing software that runs that can be compiled and run on hardware. It involves the study of the primitive operations that need to be used a lot and the optimization of those, and also the data structures that can be used to efficiently compute whatever needs to be done. At the bottom layer, it's about hardware. It's about how the software maps to the hardware, how the hardware can process what it's being told to do, and a study of where the bottlenecks occur in the software and ways to work around those. All three of these interact with each other, so how it maps to the hardware could affect the data structures that are designed for the implementations, and it could even go all the way back to algorithms and force a redesign at the highest levels. So for Spiral AIML, it's really about the study of data-intensive applications. Those applications are generally not compute-bound, they're memory-bound, and so it's often a study of how the software implementations map to the memory hierarchies in the hardware and the communication networks that are used to move the data around. We are proposing to build an automatic code generation system for these data-intensive computations using CMU's spiral code generation technology that's been developed over the past 15 years or so. For this project, we need to identify the mathematical descriptions that are used for these computational workloads. We need to develop hardware performance models for the hardware of interest for our DoD customers, especially components that satisfy cost, size, weight, and power constraints that they have. And then it's how to encode the knowledge about efficient implementations of these algorithms onto this hardware. So what is Spiral? Let's start with how fast code is traditionally done. You have domain experts that produce algorithms like synthetic aperture radar or fast Fourier transform. You need expertise in software implementations and also expertise in the targeted hardware platforms. You get all these people in a room together or a group, and after a long time, hopefully, you can produce a high-performance library optimized for that given platform. If the platform changes, then some or all of that work needs to be redone to map to new hardware. Depends on how different the hardware is from the previous approach. Now, on the Spiral side, the expertise that was put into the manual development of that software on the left, it needs mathematical descriptions of computation. Those often come from the literature and the research. And we also need to teach it hardware performance models. So how bits of code interact with the hardware and what kind of performance it can achieve. And then we also need to kind of encode the knowledge of how to implement the algorithms on the hardware into Spiral. Spiral then uses breakdown rules, rewrite rules to find optimized implementations. Quite often, it can spit out multiple candidate implementations that then need to be compiled, tested, and then chosen for the final library. The goal of Spiral is to achieve comparable performance to the large team on the left. And Spiral, for the last 15 years, has been doing this task in the digital signal processing space, and it does achieve comparable performance. And in many cases, it has actually found novel implementations that exceed the performance of the experts. So Spiral, in the digital signal processing space, understands the rules of linear algebra. And it turns out in much of the research in graph algorithms, there is this body of work that shows that graph algorithms can be done in linear algebra. It's a little different than signal processing because the linear algebra involves sparse and irregular data that's stored in these matrices. And so in a previous project, so we've been working with the CMU team for about 6 years now. In the previous project, we were working on how to teach Spiral the data structures, operations, and optimizations used in graph algorithms. Spiral needed a mathematical specification of common operations in this space. And that led to our involvement in the GraphLaws community that was trying to actually do the same thing. It was a kind of a fortuitous event. So that led to the publication of two very important documents. The first one was the Mathematical Foundations of GraphLaws in 2016, where the community laid out all of the primitives that they thought were important that could be composed to generate quite a few graph algorithms. It was only about a dozen different operations, and that's exactly what Spiral needed. That then led to the design of the GraphLaws API for the C language in 2017. And basically, the GraphLaws primitives involves, because it's linear algebra, involves matrices and vectors. They can be sparse or dense. GraphLaws doesn't care. But one of the important things that GraphLaws introduced was the use of algebraic operators called semirings. And so instead of traditional linear algebra, where you're using addition and multiplication, you can swap those out for other pairs of operations. But the fundamental operations over these objects are very similar to what you would find in any linear algebra package. They involve matrix multiply, matrix times vector, element-wise operations. You can extract subsets of the matrices into smaller ones or assign the smaller subset back into a larger one, plus a number of other. So it's basically 12 or so operations. Again, we released the first C API specification in 2017, but during the course of this project, we've released that specification 2 more times to enhance the set of operations and also to fix some things that the research community found in the spec. And actually, in the next week, we're due to release a major new version of the GraphLaws C API to address some issues that were found for those folks trying to do multi-threading, including our group. In the intervening years, so this all started back in about 2015 or so, but in the last 6 years, a number of researchers in the community have been looking at GraphLaws and using it for other things. So GraphLaws is not just for graphs. It is a very general linear algebra library for sparse data structures. Recent work by others has shown the applicability of GraphLaws for operations on tabular data like you'd find in databases and spreadsheets. That was published in a book back in 2018 called The Mathematics of Big Data. We've been looking at GraphLaws for AI, specifically machine learning workloads that use both sparse and dense data. This is an example of one of the algorithms that we looked at. We've been looking at recommender systems. And so if anybody remembers back in 2009, the Netflix, they wanted a recommender system that could predict users' ratings on movies they hadn't seen. So the input was the ratings for the movies the users had seen. And then you need to compute a dense matrix on the right of all the predicted ratings. And then for those with high ratings, then Netflix would go and recommend those movies for those users. That was back in 2009. State of the art in recommender systems these days is deep learning recommender models. And it has a mixed sparse dense workload that we've been analyzing. And this is work that was co-funded by a project that we have with DARPA on software-defined hardware. It basically looked at all the aspects of DLRM. It has dense vector math. It's compute intensive. It is well known how to map that to hardware. But it also has this sparse layer, which is lookup and embedding tables, concatenation, transposition, and all kinds of slow operations that are basically memory bound. They involve lots of memory accesses and things like that. Turns out that all of this can be expressed with the GraphBLAS math. And so this is a candidate for study in this project. So for the last 3 years, we've been looking at algorithms like this and many others. We have 3 primary lines of research and development. At the algorithm space, we're analyzing this, algorithms like DLRM and other machine learning and AI workloads. Primarily, we're doing this to identify common computational kernels and looking at how best to develop data structures that can deal with the kind of the slow, memory-intensive operations. At the implementations level, we've been expanding the GraphBLAS API. So that there have been operations discovered that are extremely useful for a wide variety of algorithms, even beyond the stuff that we're looking at, but for the greater community. We've been optimizing an implementation of the GraphBLAS math that we do here at the SEI called the GraphBLAS Template Library, or GBTL. And we've been developing an even lower level of operations closer to the hardware. And this is in collaboration with the CMU SEI department, called the Graph Kernel Collection. At the architecture level, we are taking things like the GKC, the Graph Kernel Collection, and developing performance models for multiple GPU and multi-core CPU platforms, which are of interest to our DoD stakeholders. So what is Spiral? Spiral is basically an advanced source-to-source compiler. It takes in specifications of computation, preferably in really high-level math. It likes to see linear algebra, not so much code, but it can ingest code. It takes math at the highest levels, and it goes through and analyzes the computation, builds a computational graph, and then applies a bunch of rules. It does breakdown of operations. Sometimes it does fusing of operations. It's basic, and it creates a large search space. Different ways you could break it down, different ways you could fuse, looking for an implementation that can run well on a targeted hardware platform. At the end, it spits out C code that can be then compiled for the platform. Quite often, it spits out multiple candidate implementations of the C code. So, like I said before, at the top, it takes in mathematical descriptions, and we've been using GraphBLAS math as the mathematical descriptions for algorithms in this space. We've been doing a lot of work at the lowest levels, performance models, especially for sparse and irregular workloads, and that informs heuristics for the search engine at 2 levels, at the highest levels of how to break it down, how to break down loop iterations or unroll loops. And then at the lowest levels, it provides information about hardware-specific instruction sets that could provide even greater performance to the resulting code. And then, everything is driven by an expert system on the right. There's a number of places where it can branch and search. The search space could be huge, but it does use heuristics informed by the performance models to prune the search space to produce a handful of code candidates at most. So some of the work that we've done for Spiral, I've already talked about. It can parse GraphLaw's syntax now to create the mathematical descriptions that it needs. We've had to add in support for new sparse data formats, especially the sparse irregular formats, and also the semi-ring operators. So before it did mostly arithmetic, multiply and addition, and so we've been building in the more flexible semi-ring operations. We've added computational graphs specifically for GraphLaw's optimizations. We've added bilinear representations in the middle layer, and then building in some of the kernels that we've generated for the graph kernel collection at the lowest level. So we've been at this for 3 years now, and we have a tremendous number of artifacts by this group. I'm going to break them down by the 3 lines of research and only highlight some of the most impactful stuff. So at the algorithms level, we have been analyzing a number of different algorithms. Some are listed here, but it's not just us. The greater GraphLaw's community has been doing the same for applications that they're interested in. And so the GraphLaw's community has now organized an open source repository called LA Graph. This is a place that researchers can submit new algorithms that are written in terms of GraphLaw's. The GraphLaw's committee then curates these algorithms and provides a library of robust, tested, and verified algorithms back to the user community. So it really serves 2 communities: a place for the experts to submit their code for open source release, and a place for the user community to find algorithms that may be helpful to them in their applications. The link is shown here for GitHub repository for LA Graph. At the implementation level, this is where we've been focusing on the GraphLaw's API, but more importantly, we have been developing open source code libraries. I've mentioned the GraphLaw's template library before. A major release, version 3.0, was done back in 2020. But since then, we've been developing lower level computational primitives based on an analysis of the GraphLaw's operations. Those are being collected in CMU's graph kernel collection. In the last 9 months or so, we've been re-implementing a number of the operations in the GraphLaw's template library based on the graph kernel collection, and some of the results are shown on the right. This is results for 6 different GraphLaw's operations. Speed ups using GKC and GKC approaches is 10x to 70x over the version 3.0 release. That's not 10% or 70%. That's 10 times faster or 70 times faster than before. At the lowest levels, we've been doing a lot of experiments trying to figure out where the low-level primitives are bottlenecked in the hardware. We've been analyzing both multiple CPU architectures, multiple GPU architectures. Some of the results are shown on the right for things like how to break down loop iterations to provide enough work to feed certain pipelines deep down to the hardware. In the lower right, it's an analysis how different types of sparse data structures affect performance of different primitives at the lowest levels. So that was a list of 37 artifacts, and I'm sure there are more, but that's an average of about 1 a month over the course of the 3-year project. And that was done with a large collaborative group from four researchers within the SEI collaborating with 4 professors in the EC department with various expertise in spiral, algorithms development, all the way down to hardware architectures and performance modeling. that in conjunction with their CMU staff and students that are working with these professors are the team responsible for much of those artifacts that I just went through. But it's not just the CMU team that helped. This project, which really has been going on since 2015, 2016 timeframe, has a tremendous number of external collaborators, all working on their own projects, but all interested in the graph loss community as a whole. I just want to highlight some of the more impactful results that they have done that we have built upon. One is the Sweet Sparse Graph Loss Library. It is the first conformant implementation of the Graph Loss C API that was released back in 2017. And Tim Davis from Texas A&M has been updating that package, improving it, optimizing it, making it kind of the de facto implementation for graph loss. It is now available as an Ubuntu package. And as of a number of months ago, MATLAB has been using this implementation internally for their sparse matrix algebras. On top of that are Python packages, and these have been developed as wrappers around Sweet Sparse to engage the greater data science community. Folks from Graphagon and Anaconda have both written wrappers around Sweet Sparse, and they're available with pip installs. At the application layer, a company out of Israel called Redis Labs has been developing the Redis Graph database. It's built on top of GraphLoss and is currently available in the Google Cloud Platform if you're interested in checking that out. And finally, Tim Mattson and I, Tim Mattson from Intel Research, we have been holding a series of half and full day tutorials in C and Python to engage the greater community and even grow it in members. And with that, I'll conclude my talk and open it up for questions.